Welcome, ladies and gentlemen, to another episode of Dave Does Math from Home. This is a big one. This is just about the pinnacle of university calculus. This is after Calc 3. There's no more calculuses. This is the end of calculus, and this is approximately the most difficult and most challenging and most complex section in the entire calculus curriculum. I'm not trying to scare you. I'm just trying to make sure that you know what you're getting into. This video series is going to have a few videos in it. This is not going to be a quick one. It isn't the last section we're going to do. There's still two more sections after this. After 17.6, we're going to do 17.7 and 17.8. The good news is that both of those sections are about shortcuts for doing this material easier. In the same way that in 17.2 we covered line integrals, and then in 17.3 we immediately found shortcuts for doing line integrals easier. If in certain circumstances when you have path independence, you can skip the line integral part and just do the fundamental theorem of the potential function from B to A, or from A to B. That's fine. 17.7 and 17.8 are going to be similar. It's once we learn how to do flux integrals the hard way, we're going to learn that under certain conditions we can do easier versions of the integral to get the same thing. And those are called Stokes' theorem and the divergence theorem, and we'll talk about those later. First, we need to talk about flux, which is very fun to say. This is where all this stuff gets very like sci-fi sounding and surreal. Like, we're going to talk about vector spaces, and we're going to talk about the flux through surfaces in the vector space. It's going to be very fun. I want to introduce the idea of a flux integral by connecting it to the idea of a line integral. So for that, I want to talk about line integrals. When we're doing line integrals, we have this technique for doing line integrals in 5 easy steps. First, we need to parameterize the path. We need to parameterize the path R. We need to find dr. So this is going to be a vector that describes the position of various points along a path. When we take the derivative of that, we want how these positions are changing. So like if you have a path that does this, R is like a series of vectors that point to like this point, and then this point, and then this point. And we don't want that. That's not what we want to work with. We want to work with how things change along this path, and that is dr. This is the thing we're actually going to work with. Once we've parameterized this path as a vector, we find the derivative, and that's all the little tiny chunks of path along this path. Step 3 is we're going to express f, the vector field, in terms of t. So I should say this is R of t. T is the parametric, the independent variable in this parametric thing. We usually use t there. So once we have dr, the tiny little chunks of path through the vector field, and we have a vector field in terms of the same variables, we can take the dot product to see whether they align, whether they have no interaction, or whether they oppose. Opposition, no interaction, alignment is when they both point in the same direction. So this will give us a sense of that. And then, because this gives us a sense of that for like each individual tiny little point along this path, we need to integrate f dot dr to get the total work done by the vector field along this path. So this is line integrals. and it is all about going along a path. Here's what's going to change when we start doing flux integrals. Instead of having a two-dimensional vector field and a path that goes through it, we're going to have a three-dimensional vector space, and we're going to have a surface within that space. Could be like a plane, could be a flat plane, could be a plane at a funny angle, could be a plane, could be a cylinder. Cylinders sometimes get used, big up and down cylinders like this. Could be a dome, could be a cone, could be any old surface you like. We have a lot of experience playing with surfaces in 3 space. That's what all of chapter 16, I think. Chapter 16 is when we did all the double and triple integrals and all the various coordinate fields. So we know about surfaces in 3 space. So we're going to put a surface in 3 space into a vector space, and we're going to look at the flow of the vector space through the surface. So let me use this for now. This is my marker bucket. It's a nice little bucket for markers. I'm going to extract all the markers. Let's say this is our surface. Vaguely cylindrical. I'm not worried about the top. I'm curious about the outside of the surface. If you have some vector field, like we can stick with fairly simple to conceptualize vector fields. Like let's say we're doing the explosion vector field, and we are curious how the explosion vector field pushes against the outside of this surface. That's what the flux integrals are going to tell us. That's what we're going to use the flux integrals for. And these vector fields that we're working with, when we start applying these things, I say when we start, we are not ever going to, in this class, we're not ever going to actually start applying these things because I don't know the first thing about applying flux integrals to real life situations. Please ask an electrician or an electrical engineer. When you start applying these flux integral things to electronics engineering, it's going to be because we have magnetic fields and electrical fields, electrical currents, electrical flows, magnetic fields. All of these things are things that you can model using vector spaces. And we're going to have surfaces that those things go through or go across. And you'll need to know how those things interact, how the vector field interacts with the surface. And that's what flux integrals are going to tell us. So instead of going, a lot of this stuff is going to be the same. We still have a vector space or a vector field. That hasn't changed much. We've just added a dimension to it. Instead of a path through the vector field, we're going to have a surface like across the vector field. And we're not interested in how things flow along the path. We're interested in how things flow against the vector, against the surface. So let me get my markers back in here. Hopefully I can do this without losing any of them. I dropped none of them. The markers are safe. Rest easy. So that's the general idea of what we're doing with the vector field. I want to talk a little bit about how we're going to do it. Because a lot of it is going to mirror these steps. We're just going to add a couple extra bonus steps that are going to make this more exciting. So instead of parameterizing a path, we're going to parameterize a surface. Parameterize the surface S. So the big difference here is that when you parameterize a path, you only need one independent variable, which tells you how far along the path you are. And that was our t. When we did these things, we were parameterizing things in terms of t. So when t was like 0, we were just starting at the path. And when t was its maximum value, that was the end of the path. And everything in between, t was just moving in between. It was a very simple set of parameterizations. When you parameterize a surface, surfaces have one more dimension than paths do. Paths are like one-dimensional things. They exist in like 2 or 3 space or whatever you want, but they're fundamentally one-dimensional. You just move along them in one direction. With a surface, you have to be able to move across a surface in 2 dimensions. So if you think of just a plane, you can move across this plane along x or along y. You can go in 2 dimensions here, 2 directions, 2 dimensions. So when we parameterize our surface S, we're going to have 2 variables. The book really likes to use u and v. I kind of don't like to use u and v, partly just because they look way too similar, and partly because they're not very intuitive. Most of the time, we'll be able to parameterize our surfaces using much more intuitive variables like x and y. Like if you have a surface, like we did a couple like volumes of tetrahedrons when we were doing chapter 16. So like we had surfaces like f of x, y was z equals like 12 minus 2x minus 6y or something, right? And this was our plane. It had a z-intercept of 12, it had an x-intercept of probably 6, and a y-intercept of probably 2. If you want to parameterize something like this, you can parameterize this very easily by saying that x is x, y is y, and z is 12 minus 2x minus 6y. So, if the book were telling you to do this, they would tell you to use u and v and 12 minus 2u minus 6v. And I don't think that's necessary. I think that just sticking with x's and y's so that you know which one's which, I think it's much more intuitive, much more easy to grasp this way. So this is the kind of parameterization that we're going to look for. And a lot of them are going to end up just like this, where you have some function of some variables, and you're just going to use your 2 variables like normal variables, and then for the third thing, you're going to use the function. So the parameterization has 2 variables. Choose the variables that are intuitive to you so that you can understand what you're doing, and go with that. That's how we're going to parameterize the surface. And we'll do much more examples of this as we go. I just want to do an overview of the process before we get to new examples. We're going to parameterize the surface. Step 2 is where things are going to get really out of hand. Steps 3, 4, and 5 are almost identical, but step 2 is where things get weird. We need to find both partials of S. So it's not just as easy as finding dr anymore. When we parameterized the path r, it was of 1 variable. We could find its derivative. That was really straightforward. It's pretty effortless. Here, when we parameterize a surface, it's going to have 2 independent variables. We'll have like x's and y's going on, like we saw with that thing that I am trying to point to, but I just erased. Did not plan this well. So because there's going to be 2 independent variables, we're going to have 2 different derivatives. So in the example we had before, it would be Sx and Sy. So this is the derivative of the surface with respect to x and the derivative of the surface with respect to y. And what these things mean are, in the continuing example of us using a plane, let me use this as a, that's got writing on it. Okay, this is what I was looking for. Let's use this as our plane. If this is our plane, we can move along it in the x direction, or we can move along it in the y direction. And that's what these derivatives represent. Just like I had that diagram before of the path, the derivative, when we parameterize the path, we get a series of vectors that point from the origin to the path. When we parameterize a surface, we have a bunch of vectors that point from the origin to the surface. And we don't want to go from the origin to the surface every time. When we take these derivatives, those represent moving along the surface in 2 different directions. We can move along the surface in the x direction, and we can move along the surface in the y direction. The problem is, if we're doing a flux integral, we don't want to be moving along the surface at all. we want to be going through the surface. So the vector that we want to use to represent things going through the surface, we want to get the normal vector. Normal is a fancy geometric word for perpendicular. We don't want vectors going along the surface this way or along the surface this way. We want them coming out of the surface, through the surface, perpendicular to the surface. And the way we get that is we have to take the cross product of these two derivatives. We know from chapter 13 that cross products, the cross product of two vectors, if you have two vectors doing things, cross product is the vector that's perpendicular to both of them. And that's what we want here. One of these vectors is going across the surface in the x direction, one of them is going across the surface in the y, one of them is going along the surface in x, one of them is going along the surface in y. And we don't want to go along the surface at all. We want to go through the surface, across the surface. So we need to take the cross product of these two along the surface vectors, and that'll give us our normal vector. So that's how we get our n. N, the vector normal to the surface we have parameterized, is what we're going to use for our flux integrals. So a little more work here than normal. Step 3 is exactly the same. Express f in terms of the parameterization you used here. So if your parameterization used x's and y's, then you have to express f in terms of x's and y's. It's probably already in x's and y's. But if there are, for example, z's in your f, and your surface is expressed in x's and y's, you need to transform all the z's in your vector space into x's and y's as well. But this step is a pretty close mirror to this one. They're about the same. We need to take the dot product. Once f is expressed in terms of the correct variables, we're going to find the dot product of that and the normal vector. Again, we're not going along the surface anymore, we're going through the surface, so we have to use the normal vector here. So steps 3 and 4 are essentially identical to these steps of line integrals. They're not so bad. Step 5 is a little bit different. When we get to step 5, we again run into this problem where we have two variables. So here we have to do two integrals. We have to do the double integral of f dot n. This is usually written as like ds, but again, like if you're using x's and y's here, this ds will be a dx dy. So when you parameterize your surface, there's going to be some bounds involved. You're going to have bounds on x, bounds on y, or whatever other variables you use. Sometimes we'll use like thetas and phi. Sometimes we'll use, maybe sometimes we will use u and v. But whatever variables you use, there'll be bounds to determine the edges of your surface. Those bounds become the bounds on your integral, and you integrate with respect to those variables once you have this dot product of f and n. So, same basic structure of a plan with just a couple more exciting elements going up. We've got a surface instead of a path, we're going across it instead of along it, and we're doing a double integral instead of a regular integral. Aside from that, flux integrals are exactly the same as line integrals in terms of what we've already done, and they are not as intimidating as they look. They do take a while, I won't lie to you about that. There are 7 questions on this homework assignment. It took me about an hour to finish. So get started on that pretty soon. But they're very doable. They're just kind of long. I'm going to cut this video here. We're going to start part 2 with some examples. I have lots and lots of examples to go over, so stay tuned.